So the general most common way of doing this, like 99.9% of statistics, is to exploit asymptotic normality to figure out the standard error. So what do I mean by that? Well, a ton of estimators, basically any estimator that you will ever see out in the wild, has a normal sampling distribution. And the reason this is because if it doesn't, then it's not useful because you can't, it's very, very difficult usually to figure out its standard error, so nobody uses it. So basically anything that anyone uses has a normal sampling distribution. And there's also other reasons which are more like mathematically that so estimators tend to have this this kind of sampling distribution. So it's actually quite hard to make one that isn't asymptotically normal in the first part, and then two, if you did, it would be typically useless. But so back to the point here. A lot of estimators do have a normal sampling distribution for large n. So what do I mean by that? So here, let's say x is, you have n data points. They're all IID from this weird beta distribution. And here, my estimator is just the sample mean of those things. So maybe the estimand is the true mean, and I'm trying to estimate it just by taking the sample average of our data points. So if I look at the sampling distribution of this thing, right? So here I have what the experiment I did here was I generated two samples from this, so two x's, and I took their mean, and then I generated two more and I took the mean of those, and I generated two more and I took the mean of those, and so I'm going to have a whole, like, however many times I do this, like 10,000 times, I'm going to get 10,000 estimates, and then I'm making basically like a histogram of those estimates. And what I see is that if the number of times that I'm sampling is 2, the sampling distribution of my estimator can look kind of wonky. But as I increase it, as I increase the number of samples that are in my data set, in each data set, which I'm repeating multiple times, as I increase the number of samples in each data set, the sampling distribution of this mean estimator becomes very bell curve shaped. And here it happens even just with n equals 20. You're already getting something that looks a lot like a normal distribution, just to the eye. And this happens for a lot of different estimators. We looked at this a little bit last time too. So here's a much more complicated data generating process. So here's a multivariate. We have 3 different random variables and all their conditional distributions. So these two, w and y, are not even continuous. They're discrete. X is continuous. And they have this this logistic function, how they relate to x. So this is complicated. Our estimator is also complicated. Here, this is an estimator for the risk ratio. So we're looking at this is the plug-in estimator for the risk ratio. So we're looking at the sample average of y among those people where w equals 1, and comparing that to the sample average of y among those people where w equals 0. So you know this kind of thing would be, maybe you want to know, like, what's the rate of disease among a population that is getting one exposure versus the rate of disease among a population that's getting another exposure. That's typically what this kind of thing is used. Of course, you don't know those true population rates, but you can estimate them from your whatever small data set you have. And this is the estimator that you would use. This is the plugin. This is one that you might use, I should say. And how does this estimator behave? Well, if your data, there's only 2 samples in your data, and you could hypothetically, if you knew the data generating process, of course in practice you don't, but if you could, you could repeat the experiment, draw 2 more data points, calculate this thing, draw 2 more data points, whatever, so on and so forth, and you would get this sampling distribution. So I did this in R. You can do this too. But if I increase the number of data points that I'm drawing in each of those data sets, then by like 150 here, again, this is starting to look very bell curve shaped. So why is this useful? Well, because bias and variance fully describe the distribution of an asymptotically normal estimator. So if I know that this is asymptotically normal, there's only 2 things I have to care about: the variance and the bias. Okay, so I don't have to worry about anything else. The other interesting thing about asymptotically normal estimators is that as n increases, the thing to notice here is that variance gets smaller. So here's another example where I have, I believe this is just a sample mean, but for n equals 20, I have this kind of bell curve that looks like this. As I increase n, it gets more and more peaked, which kind of makes sense. Like, I mean, if you have an estimator and you're using a ton of data, your guess should be more precise if you're using more data, right? If you have, so that is like, so here the right answer, so to speak, is 0. That's the true value of the estimand. If I only have 20 data points, sometimes I randomly get a data set where it looks like that mean is like 0.4, right? Just randomly. Because, basically like one data point, right, out of 20 could kind of throw it all off. Whereas if you have 1,000 data points and you're taking the mean of them, it's very unlikely that you're going to get a mean that's too far away from 0. That's the basic idea here. And so with these asymptotically normal estimators, the only thing that's changing as you increase n is this variance, because there's only variance and bias, and this variance is decreasing. So you're getting a more precise estimate. How does it decrease? Well, it turns out that it actually decreases like 1 over n times some constancy. So I'll show you what I mean by that. So like here, if I look at, so let me go back here. So if I look at this estimator, so n equals 100, 200, 300, 400, whatever, 500, I can actually just measure what is the variance of each of these. So you can do this in R just by taking the sample variance of the sampling distribution as you increase n, and then what you can do is you can make a plot. So you can plot the sampling variance. So that's what I've done here. This is the pink line. I'm plotting the sampling variance as I increase n, and this is the shape I get, is this kind of pink line. And now what I'm showing with these gray lines is that this pink line actually has the same shape as these gray lines, and the gray lines are just 1 divided by n times some constant. So this one is for c equals 5. So this is basically 5 divided by n. This one is 4 divided by n. This one is 3 divided by n. So what that's showing is that this pink line is something like 3.5 divided by n, is like the function that describes this pink line. Why does that matter? Why do we care? Well, if what we're saying is that the variance of this estimator, so here I've put the little n as a subscript to kind of say, is it this one or this one? Like, how big is the data that I'm using? So if the variance of this estimator is proportional to some constant over n, then we can multiply the n on the other side, and then we can pass that n inside. So remember, this is one of the rules of variance is that so we saw that if you have a times x and you want the variance of that, by the properties of expectation, you can pull out the a, but it has to be squared. And that's basically because variance is like the expectation of some squared thing, and then expectation is linear, so you can pull out the constant. So this is true, and so here in this case, if you take a to be square root of n, then if you take a to be the square root of n, then a squared is n after we've pulled it out. But we're just going the other way, so we're putting it inside instead of pulling it out. So that's just from properties of expectation. But what this says then is that if you take this estimator and you blow it up by root n, so this is like you get whatever your mean is, and then you just however many data points you had, multiply that, take the square root of that, multiply it by that mean, and then look at the sampling distribution of that thing. As you increase n, the variance of that sampling distribution will be constant. So this is always the same. And that number, whatever that is what we call the asymptotic variance, or asymptotic sampling variance. And so you can write kind of informally that your estimator has this distribution. The sampling distribution of the estimator, it's normal. It has it's the mean mu, and it has the variance is just going to be given by this asymptotic variance divided by however many data points there are. Or another way of writing this, so if you kind of subtract the mean and then pull out the variance, divide things, you can also write it like this. So you'll often see this kind of stuff where you'll have root n times the difference between your estimator and its mean divided by this asymptotic standard deviation is a standard normal. So I'm showing you this just because sometimes it's written this way in like stats literature, and like really this is the kind of correct way to write it. But it can often be confusing. Like, where the hell is this root n coming from? What's going on? And so I'm just trying to demystify the notation a little bit. So all this says is that this estimator here has a sampling distribution that where as you increase the number of data points, it looks more and more normal, and that sampling distribution is kind of shrinking down. But there's some kind of constant where if you blow it up by that constant, happens to be root n, then you get this sampling distribution with this constant variance that we call the asymptotic sampling variance. So what does that mean? Why do we care about the asymptotic variance? Well, because if we know what that thing is, and that's a property of the data generating process, and we know how much data we're getting, all we need to do to get the standard error is just divide it by root n. So then that's kind of nice. So this kind of removes the dependency of calculating the standard error on the sample size, and it says, well, the only dependency on the sample size is this factor of root n, and everything else just depends on the data generating process when it's like IID, how that data generating process works for a single observation. All right, so that was a lot, but in your own words, let's think about what. I just want you to think about what's nice about estimators that are asymptotically normal. Let's just summarize what we've gained here. So I'd say, firstly, everything we need to know is everything about the sampling distribution. You can boil it down into two numbers, just the mean and the standard deviation. So that's kind of nice. Next thing that's nice about these asymptotically normal estimators is that the standard deviation at any sample size is just going to be given by this asymptotic sampling variance divided by root n. So we don't have to really worry about how this data generating process, how n factors into that. We can just think about the DGP for a single observation when it's IID.